Welcome to Ask and Learn.
So for this problem, you have two concentric spheres. And then let me just say, I love this problem. No numbers, keep it nice and simple. And the first one has a radius A, second one has a radius B, charge QA, charge QB. And then the questions are basically find the field in all the regions. Let me do this all in black. So for A, you want to find the field within the first shell. So the idea is if you draw a Gaussian surface within, i.e. a spherical shell, so the Gaussian surface, right, for a spherical asymmetric charge distribution is always a sphere. So if you draw a sphere within the sphere A, basically, then you're not enclosing any charge. So by Gauss's law, the electric field is 0. For B, it's within between these two, and then you would draw your Gaussian surface like this. So it's always, of course, it would be a sphere. And then you would say basically that Gauss's law says, right, that the flux, which is the integral of E dot dA, is Q enclosed over epsilon naught. The integral of E dot dA is just EA. And then A is the surface area of the sphere of your Gaussian surface. And that's Q enclosed over epsilon naught. And A is 4 pi r squared. So E 4 pi r squared equals Q enclosed. That's just QA. But if you had like a charge in the center, for example, you would do QA plus that charge. Of course, divided by epsilon naught. And then now we can say that E equals Q and not enclosed. Oof, oof, oof. It's stuck in my memory. All right. Great. So it's E is QA over 4 pi r squared epsilon naught. And for C, I'm just going to kind of skip this part because it's the same thing except for your Gaussian surface is now like out here. And now you've just enclosed all of the charge. And so your QA just goes to QA from QA to QA plus QB. So QA plus QB divided by 4 pi r squared epsilon naught. And for D, it's a discussion, so I'm not going to like write up the answer. I'm just going to discuss it. So I'll put listen just in case it's useful. Okay, so you want to get the charge distributions on the inner and outer surfaces of shells. So let's talk about that. So, okay, QA, so the charges, first of all, always, for conductors, always go to the surface. So for this inner shell, then QA is going to be on the surface of that, and then it's going to polarize the outer shell. So QA is going to be, negative QA is going to be on the inner surface here. That's because if you drew your Gaussian surface within the shell, the electric field would be 0 because it's a conductor, and then by Gauss's law, you conclude that the total charge enclosed must be 0. So the inner surface must match this outer surface. So it should be minus QA. And then you would just need to figure out what charge would go on the edge to make the total charge QB. So for example, if QB was 0, then you would have positive QA on the outside to balance, such that the total charge would be 0.